Hello and welcome to my video, lesson 9.2 on trig identities, but especially the Pythagorean identity and identities. So it comes from the unit circle. So it comes from this idea that as you go around the unit circle, every time we make a triangle, the triangle is the hypotenuse, which is the C side when we talk about a squared plus b squared equals c squared. But the hypotenuse is 1 because it's the unit circle, so it's the radius of 1. Okay, well that's great, but that means that this is x and this is a y value for this coordinate, right? And we already said that we know x and y in the last unit. X is cos of the angle and y is sine of the angle. So if we use that logic, yes, it's here, but in the unit circle, it's going to be this one. And going one step further, instead of x and y, we'll use sine and cos. And so we get this statement as our Pythagorean identity. Okay, so that's from the unit circle. So if we know that to be true, and we know all of our reciprocal and quotient identities from the last video, and you can always reference your formula sheet if you're unsure, then we should be able to prove the following identities, or express the top identity, the original one, into these other forms. So let's see if we can do that. So what we're going to do is kind of move things over a little bit. What we're going to do is divide this original one. So we're going to take this and we're going to divide every part of it by what? By cos squared theta. Every single part. Okay, and if we do that, you'll hopefully notice that these two cancel out, and this becomes tan squared theta plus 1, because they cancel. Canceling doesn't mean they disappear, it just means they go to 1. And then on the right side, it's secant squared theta. So this is the quotient rule on the left for tan, and then for secant, it's the reciprocal identity. Okay, really cool, pretty simple. What if we do this backwards? So what if we just do the same thing, but instead we divide by sine squared theta for every single part? Well, hopefully you can see right away, if we're going to do that, the first set is going to cancel, just like it did before. But this is going to be the reverse of tan, which is 1 over cotangent, or sorry, it is cotangent, 1 over tan, which is cotangent, and then this is going to be cosecant. So they're just using the original statement from the unit circle and then creating these other two. The other two may come up. They don't come up very often, I'll be honest. And also, if I were making the formula sheet, I wouldn't give you the other two because they're so basic based off of what we already know. But that's okay. You are given those in your formula sheet. So let us continue and try to prove these following statements using the same logic. Okay, so prove that sine to the fourth theta minus cos to the fourth equals sine squared minus cos squared. So there are multiple ways to try to do this. But what we're going to do, so first of all, it says prove. So what we're going to be doing is the left side equals right side thing that we did in the last video. And in this case, you hopefully can see that this is actually a difference, subtraction, of squares. So another difference of squares. So let's go ahead and just do the left one first because it's to the fourth and see what we get. So if we recognize that's a difference of squares, this is sine squared theta minus cos squared theta. And then it's sine squared theta plus cos squared theta. So you square root each term, and then you do a positive and negative version of the binomials. And that's fine, but we can now use our Pythagorean identity from up above, which looked like this to start. And we can take this and rearrange this. Now, I don't think it really matters which version you do, but I'm going to subtract the cos across. And so what I can do is, instead of sine here, I'm going to write 1 minus cos squared theta. So this left-hand binomial is going to stay the same. But this part in blue is the identity that we're using. Okay, and now if we look at that, hopefully you can see that these two are going to cancel, and so that whole thing just turns into a 1. And 1 times whatever is just same as what it was before. So sine squared theta minus cos squared theta. And now we can finally say left side equals right side. All right, so we've done one proof now using that Pythagorean identity. Let's continue on to some other examples. So here we have an example where we're going to see something happen that happens somewhat commonly. You can do this in either direction, but I'm going to do it on the right side because this is what we're used to when we're rationalizing the denominator. So here we have this statement, but when we rationalize the denominator, which is that's not what we're doing here, but we're going to do something similar. We multiply by the conjugate. So that's what we're doing here. Now, if we multiply on the denominator, we have to multiply on the numerator. Otherwise, we've changed the actual value, so we don't want to do that. But when you do this multiplying by the conjugate thing, what's really nice is that the middle term of the binomial expansion disappears. So this is going to be 1 minus sine squared theta on the bottom. On the top, I'm actually not going to change it at all. And you'll hopefully see why in a moment. Because the top already kind of looks like the left side, almost, except for that cos. Okay, so now what we need to do is notice that that cos squared theta equals 1 minus sine squared theta from the Pythagorean identity. So we're going to put that in at the denominator. So I'm just rewriting out the numerator now. And then the denominator is cos squared theta because we've replaced it from here. And then you can see that one of these at the bottom cancels with this one on the top. And so we have to just rewrite it out one more time. 1 minus sine theta over cos theta. And you can see that my left side equals my right side. All right, so whenever you see this 1 plus sine or cos, it's something to watch out for. Alrighty here. So what we're going to do is take a look at the next proving statement here. So we've got these two sides, left side and right side, and we're going to try to prove them in the same sort of idea as before. But these ones are actually, I think this is going to be a little bit nicer to work with. So the right side, what we're going to do is, I hate reciprocal functions. I'm for sure going to change this to 1 over cos squared theta. Makes it much better. But on the left side, we need to have common denominators to be able to add two fractions. So to get common denominators, we're going to have to multiply by the other denominator. So let's write it out nice and carefully. So 1 minus sine theta over 1 plus sine theta times 1 minus sine theta plus, and then on this side we've got 1 plus sine theta, and then here we've got 1 minus sine theta, 1 plus sine theta, which obviously the two fractions have the same denominator. So what we can do is rewrite it out. So it's 1 minus sine theta plus 1 plus sine theta. But the denominator is going to be just multiplying two of the binomials together. So it's going to be 1 minus sine squared theta, because of the same kind of difference of squares, or difference of squares rule or conjugate rule that we had before. Now, the same rule as before, 1 minus sine squared theta is going to turn into cos squared theta on the denominator. And on the numerator, you can see that the sine and sine are going to cancel with each other. And so by doing that, we're going to end up having a 2 here. Actually, it looks like this is kind of a funny question because does my left side equal my right side? No, because they are slightly different from each other. So they're very, very close. And if there was a 2 here, 2 secant squared theta, then they would be proved just now, but they're not. And so you should always, this is why we always need to think about that final statement, left side equals right side. Make sure you've actually checked that at the end. 9 times out of 10, it should actually be an identity. This shouldn't really happen. I think this is my own mistake when I made this question, but it's a beautiful mistake because it allows us to notice this. All right, sorry, I had to make a little bit of an adjustment to this question here. So this is our statement, and now we're going to go ahead and try to prove it. And just keeping in mind that it says determine non-permissible values on this question. So we do need to look at that as well. So let's go ahead and try to solve this. The first step here is hopefully recognizing that this is one of our Pythagorean statements. So tan squared plus 1, that's right here. That equals secant squared theta. So that's going to turn into secant squared x plus tan x secant x. When I do this, normally I would just be like putting in sine and cos instead of using that Pythagorean identity, but may as well do it because we can see it here from what was said before. On the right side, I don't really think I want to touch that yet. It might be useful, but I don't know yet. What we're going to do is change all of this into sine and cos. So we're going to go 1 over cos squared x plus sine x for the tan, and then the sine x over cos x is the tan, but the secant is also there, which is another cos squared, well, cos x, which eventually will make both of those squared. So the denominators are actually the same. So it's cos squared x, and so we can just add the numerators, which is 1 plus sine x. And actually, it ended up being a lot less work than you'd think, given how big that initial expression is. Left side equals right side. Okay, and we want to figure out the non-permissible values. So how can we do that? Well, what we're going to do is look at whatever is on the denominator. Now, in all of these cases, it's only just cos on the denominator at any point. So we don't really need to worry about all of the other possible things. It's cos on the denominator. So if cos x cannot equal 0. Okay, that is our restriction. But how do we want to write that? We want to think about it on the unit circle. So we did this in the previous video, but I'll show you again here. Where is cos 0? Well, cos is 0 up here and down here. That's at 90 degrees or pi over 2, and at 270 degrees or 3 pi over 2. So x cannot equal pi over 2 plus pi k, where k is an integer. And this is our restriction. So what that is saying is we start here, then we add a pi, so we get to here, then we add a pi, then we get to here, back and forth, or you subtract back and forth, back and forth. All right. So I hope this video helped you better understand especially the Pythagorean identities, and good luck.